Okay, so in this particular lecture, we look into the what we call the background-oriented Schlieren. So the principle is essentially, whatever we have learned so far, it's like this. So say you have a room or you create a background. So what happens is that you take an image in the absence of the flow or in the presence of the flow. So you take two images. Okay. So what we do essentially is that you use a random normal distribution of dots to create a structured background, and then you use any cell phone or normal cameras to image that particular of the flow. So what we do is basically you have a screen and you have a camera. So first you take an image of the background. So the background, which is the screen, can have different textures. It is usually textured, so it could be like a dotted wall or something like that. And then you introduce the object of interest, which in this case is a flow. So it could be like a wind tunnel, it could be a cup of tea, it could be anything. So the object of interest where there is a density gradient present. As a result of that, you will have some distortion of the dots essentially, or using then some image convolution, then we try to find out that what will be the actual flow situation. So this is what essentially the crux is of background-oriented Schlieren. So what we have over here, if you look at this is the principle. So you have a density gradient. This is the object of interest. This is the background plane. And this is the image plane. And this is the XYZ coordinates. What happens, and this is taken from Venkat Krishnan and Meyer's experiments in its paper in 2004, highly cited one as well. So what happens is that this is the checkered surface. And the same form where n minus 1 by rho is equal to g by lambda, this is still valid. So first, these are the equations that you have seen already. So because of the presence of this density gradient, we get an image displacement, which is epsilon. Now this image displacement, which is 1 over n naught multiplied by the integral of the variation of n in the y direction, okay, and then you are integrating it across z, which is in this particular direction, okay, and it is integrated from z d minus delta z and then a plus delta z. So if there is a image displacement of the background plane, okay, that translates to a virtual image displacement here, okay, as you can see, and they are related by the corresponding distances, right? So delta y prime by zb is equal to delta y by zi. Okay, zi is equal to the delta y per se by the f, which is the focal length. Right? Now for small deflections, your epsilon is given by delta y prime by zd, which in other words translates to delta y into zb divided by zd into f, or in other words the sensitivity, that means that delta y by the grad of n is equal to or almost equal to the zd into zb, okay, multiplied by the focal length, which is f. So if you look at this now, okay, so this is what you are going to get. Okay, so where this is now, this background oriented Schlieren technique is therefore based on the same relationship between the refractive index of a fluid given by the Gladstone-Dale equation, especially for gaseous medium, and this is also compared with laser speckle density photography sometimes. Okay, but if we see that here the main purpose is that the reference image is generated by recording the background, which is observed through air at rest, And the second step is an additional exposure, which introduces the flow under investigation. Okay. Now, the deflection of a single beam contains information, therefore, about the spatial gradient of the refractive index, which is integrated along the line of sight. Okay. So, in other words, for small angle deflections, okay, your this is what you are ultimately going to get. Okay. So the image displacements are given by this set of equations, right? These are the set of equations that actually tells the whole story. Okay. So in other words, you can do that. What in the principle is, now we can get the displacement in the XYZ directions to the cross correlation of the images, and this corresponds to the first gradient of density in X and Y direction. This is what we are stating, that each point is deflected, and so there is of course an X and Y of this plane, and we record all of them, and then if we deconvolute, you are going to get these are going to correspond to the first gradient of density in the X and Y direction. I mean, that is essentially what you are getting. So this is, for example, in the Y direction. All right. So this is shown in one particular direction only. Okay. But it is prudent to convert this to a field equation now. So if you convert this to a field equation, you get a Poisson's equation. Now this Poisson's equation essentially tells that, if you take the Laplace of the density field, which is X and Y, okay, that is equal to some source function in this particular case. So this is the net equation that you are going to solve. So the calculation of the line of sight integrated density field using line integral or using the solution of the Poisson's. So these are the two ways by which you can calculate. One is basically the line of sight integrated density field using the line integral, which we just covered. Okay. Other one is using the solution of the Poisson's equation, where you solve for the density field. Okay, and once you solve the density field, you can calculate, the rho is calculated is in the projection plane, and that leads to the density field in the object plane. All right, so this is a little bit of a relatively easier way to calculate. So the background oriented Schlieren therefore gives us two interesting insights, right? So this particular technique actually allows us to get a field measurement, okay, and get a more what we call quantitative measurement of the flow field in question, because we are dealing with flow fields over here. So in other words, what this background oriented technique, how it is different, is that it uses the correlation techniques on a background dot pattern to quantitatively characterize, any mildly compressible or thermal flows with good spatial and temporal resolutions. The main advantages are basically experimental simplicity and the robustness of the correlation based digital analysis. That means this is therefore routinely used in many of the application contexts, right? So that is what it is. But because of the line of sight integrated density field, the natural question is that can we extract, kind of do some kind of a tomography, which is what I would say extracting three-dimensional features. Okay, so three-dimensional density fields. If we use multi-camera recording and if we do tomographic evaluation, okay, so it is generally therefore should be possible to do some kind of a tomography, okay, for this. Okay, like we said that in the case of the determination of 2D flows, like what we have shown here, we use, for example, a Poisson solver to integrate the density gradient and determine the relative density of the field. Okay, so but however, this any non-2-dimensional nature of the flow field will distort the results. And because BOS is a line of integrating technique, so therefore, you need more tomographic techniques for the three-dimensional flow, three-dimensional, or tomographic algorithms, basically to actually do that. So this leads to how you can do that. You can do through image construction. So there are plenty of ways to do that. You can do brute force inversion technique. You can do iterative techniques, or you can do Fourier techniques, which can have a background projection technique or a filtered back projection technique. Okay, so there are a lot of ways in which you can actually do that. Okay, so in the case of axisymmetric flows, this becomes a little bit easier, but in the case of highly 3D flows, it's a little bit more complicated than that. So the main people on the tomographic brief history was Johann Radon, who worked on the calculus of variations and differential geometry and measurement theory. And the Nobel Prize in Medicine for CAT scan essentially went to Alan McCormack and Gottfried Hounsfield. They were physicists and an electrical engineer. They got the Nobel Prize in physiology or medicine. So this is a brief history. So this is used even in X-ray tomography and stuff like that. So the essential heart of this is a Fourier slice theorem. So what happens is that if you assume that fxy is a two-dimensional, real field or a function in the xy coordinate. Now this can be your flow of interest, and say L, these are the L's which are like at some angle theta with respect to this. So this is like a projection plane, right? A directionality is introduced. So if this rays actually pass through it, now in some cases, for example, in X-ray, what will be the absorption profile that you are going to get in this particular projection plane? In this case, of course, what is the distortion of the rays or the deflection of the rays because of this? Now, since and the ray is therefore described by a simple function like x cos theta plus y sin theta equal to rho. Now, what happens is that since rho and theta can be any real values, so theta and rho can be any real values, the integral of fxy along the ray, which is L rho theta, which is now given as L as a function of rho and theta, defines a 2D function, which is denoted by G rho theta. G rho theta. Okay? We call that G rho theta, the Radon transformation of xy, of fxy. So the Radon transformation is basically what gives you the G rho theta is equal to the Radon transform of fxy. Now this transform, if you open up, it is basically nothing but fxy multiplied by delta into the whole term into dx into dx into dy. Okay, this ultimately gives you the G rho theta, which is what is the intensity of the deflection at this end. So you basically take a slice along the ray direction, and then you kind of determine that what will be this transform. So now that we have got this, okay, the Fourier slice theorem now forms the basis of parallel beam filtered back projections and fan beam filtered back projections. Parallel beam is the one that is of most interest. So the expression is that the 1D Fourier transform of a projection with respect to rho and given value of theta is given by G omega theta is equal to that G rho theta into this, right? So substituting this in the earlier equation, now you basically know what your G rho theta was. If you look at this, this is what your rho G theta, G rho theta was. And so if you substitute it here, we'll have the G theta given by the triple integral, and this is equal to this. So this G is a Fourier transform of the projection. So if this is the projection, this is the Fourier transform of the projection with respect to rho and given value of theta. So for a given rho theta condition, this is what you are actually going to get, and you are substituting basically whatever was inside. Remember the Radon transformation, and then you get this entire quantity. Okay. So now by replacing u is equal to omega cos theta and v equal to omega sin theta, you get this value of g omega theta. The above expression is basically recognized as a 2D transform of xy evaluated at certain values of u and v indicated. Okay, so in other words, g omega theta is nothing but the 2D transformation of fxy evaluated at u and y. So that FUV therefore denotes the 2D Fourier transform of fxy. Okay, so this is what you get, transformation of fxy. So you see that so g omega theta is therefore FUV evaluated at a certain value of UV, which is nothing but the 2D Fourier transformation. So the above equation is known as the Fourier slice theorem or the projection slice theorem, which states that the 1D, this is important, 1D Fourier transform of a parallel projection is equal to the slice of the 2D Fourier transform of the original object, because you are evaluating it at a certain u and v. Okay, so the Fourier transform, so understand this, the FUV is the Fourier transform of xy. So FUV, which is evaluated at a certain value of u and v, is basically a slice of the two-dimensional Fourier transformation of the original object. Now this is equal to the one-dimensional Fourier transformation of the parallel projection, which is essentially this. Okay, so this is nothing but the 1D Fourier transformation of the projection, because that is what we did over here. It's a 1D projection. So this is the important part, that one-dimensional Fourier transform of a parallel projection is nothing but if you take the two-dimensional Fourier transformation and take out a slice at a certain value of u and v. All right. So this actually implies that, you know, if you are going to take, for example, this is one projection, okay, which is evaluated at a certain angle. You can have a projection which is evaluated at a different angle, and these are the corresponding Fourier 1D Fourier line transformations, right? So in other words, if you now reconstruct the function, okay, so this is the inverse 2D Fourier transformation of the 1D Fourier transformation of the projection. So this is essentially what you are going to get. So this is, for example, the 2D Fourier transformation of FUV, and then you take at a certain value of f, a certain value of u and v. Okay, you take out those slices. So this is almost like the 1D Fourier transformation of the projection. So this is very simple. So these are the number of projections that you need. So how many projections do you need to reconstruct this whole thing? So if you have, for example, in the Fourier plane, so if you have a low spatial frequency, you ensure that there is a smoothness of the surface, but you miss out on a lot of information. Okay, if you have a high spatial frequencies, you get details and sharpness, but high spatial frequencies is relatively weak reconstructed image, and they may appear to be blurred. So in other words, low frequency means that you are using a smaller number of projections. Now high spatial frequency means that you are having a higher number of projections. Okay, so this solution of this, you know, blurring and the weak reconstructed image is done using a filter. So this is the filter. This is where you introduce the filter, okay, in this whole thing. Okay. So these filters are of different kinds, like the Lack filter, the Logan filter, the Hamming filter. So the individual back projections at an angle can be obtained by convolving the corresponding projection and the inverse Fourier transformation of the Ram filter. So this gives rise to the sharpness, essentially. Okay, so this is the important line, that the back projections at an angle, which is what it is, can be obtained by convolving the corresponding projections, which is g rho theta, multiplied by the inverse Fourier transformation of the Ram filter. So this is the Ram filter. Okay, so this is what is done to get a better imaging quality. Now this can be done with the type of projections. Now this is what is the parallel beam projection. So these are at different angles, as you can see. Okay, so different theta 1 and theta 2. So parallel projections are given as parallel integrals, as is given by g rho theta for a constant theta. Okay. Then you can also do fan beam projections, where these are kind of fanning out because the line integrals are measured along the fans. Now this can also be done, but it is preferable to use something like this in the cases I'm concerned about. So examples of projections from known images. So for example, if this is an image, and then you take projections, say this is at 45 degree, this is at 90 degree, this is at 0 degree. So you take projections at different images, different planes, right? Now, if we do 4 projections, so this is the original image. So if you do 4 projections, you get an image which is totally off. This is 12. This is like 179 projections, which is basically quite a lot. If you use a Ramlack filter, then you almost reconstruct this whole thing. Okay. So as you can see, the higher the number of projections, better it is, but there is incidental blurring and loss of image. So if you use a Ramlack filter, you can get an image which is pretty much of the same quality. So this is what is exactly done. Okay. So the choice of background, therefore, you should choose a high contrast, a high background contrast. Okay. And the feature size of the background is of interest. You should have uniform distribution, and you should have 3-dimensional effects within the background in case of a natural background. So this can be different things. This can be random dots, natural background, which can be like a textured wall, for example. If you have a colored background, if you have a retroreflective background, if you have a multi-level feature background, all these are the choice of backgrounds that you need for the BOS. The camera is usually scientific grade cameras like Phantom and Photon, or DSLR cameras are also okay. You can have a high framing rate or a normal camera depending on your requirement. The resolution in terms of pixels, higher the resolution, better is the spatial resolution that you can do. Aperture control is better for the sensitivity, the minimum location of f, which gives the better sensitivity of the system. Now, if you look at this, you will just recall that f was here, so the sensitivity can be tailored according to your application. So, and then of course, the minimum aperture is required for high light intensity, and it's a trade-off with respect to the hardware availability. You could have continuous and pulsed light source depending on the flow field that you are concerned with. So there are varieties of things. For example, this is an experimental setup. This is the background. These are the Schlieren windows. This is the camera. This is the light source. So this is the background image with and without flow. So this is also taken from Venkat Krishnan's work. And this is the calculation of the density gradients by estimation of the background displacement. Here it is used, a PIV type cross correlation algorithm has been used. So you can see the quantification now starts to happen over here, which was the requirement, as we said. And the procedure, as we said, that the calculation of the line of sight integrity by the solution of the Poisson's equation. In this case, it's a 2D flow field. So you solve the line of sight integrated Poisson's equation. So you are seeing inside the depth of the board, essentially. So that is what you are trying to see. And reconstruction of 3D field by a filtered back projection, which we kind of did using a Shep-Logan filter with 2 as a projected data set. So this is the reconstruction of the 3D field. This is the 2D line of sight integrated density field by the solution of the same equation that we covered earlier. And okay, so this is the mean density field in the field that is of interest, that is extracted out in a particular plane. Okay. So the BOS methods, therefore, in a nutshell, is obtain images of a structured background in the absence and the presence of a flow field, then calculation of the density gradients by using estimation of background displacement using a PIV type cross correlation algorithm. We use the calculation of the line of sight integrated density field by the solution of the Poisson's equation. The mean density field in the plane of interest is obtained by a filtered back projection of the algorithm using the Shep-Logan filter with LOS with LOS data as the background set. So there are varieties of other, measurement ways in which you can do this. This is, for example, Schlieren, which shows the mark angle and angle of attack along the minor axis, along the major axis. So you can get very highly constructed three-dimensional data. And this is, of course, the quantitative density field, which is also calculated in a very similar fashion. Okay. These are some of the Schlieren experiments where you can see that it is very high speed, where it shows the detonation, microblast detonation, using detonation mechanism. So this is very commonly used. This is from Venkat Krishnan's work, which is the density field of a micro explosion using a background oriented Schlieren in this particular case. This is another work, which is discrete time BOS results, which shows this the mark disk, the barrel shock, and a lot of other cool stuff over here. So all these things, as you can see, these are kind of well understood. In future, of course, BOS can also use machine learning because this makes for a test case for machine learning. This is from Jiang's data, for example, which is the reconstructed density field. So you can see that BOS is can be used for a varieties of purposes. It's an extremely robust method, and it's simple compared to other types of imaging techniques. So one can also use BOS data for machine learning, for flow reconstruction or flow prediction purposes, the ways things are going. I think this is one of the major areas of improvement, or the major areas of research that will happen in due course. Thank you so much.